Lecture 8, Memory, Segmentation, and Paging. In a lot of the discussion that we've talked about memory, there's been some different ways of thinking about it, right? I say, well, memory is a linear array of bytes, but we've also been told there's the stack and the heap, and that there are libraries, there are instructions, instructions data, these kinds of things. It's not always entirely clear, and well, both of these things are true, right? We're just looking at memory at different levels of abstraction in each of those, and based on those levels of abstraction, it leads us to slightly different conclusions about the way that memory is. Right, at a low level, it really is a linear array of bytes, but there are logical subdivisions that are on top of it, and, as Ben Kenobi would say, so what I told you was true from a certain point of view, although maybe I was less cryptic about it than certain deceased Jedi masters. Okay, so the thing about it is that memory is frequently sort of logically divided up into different areas, and each of the elements, like the stack, the heap, whatever standard C library is sort of loaded into things, all of those are segments, right? And programmers don't necessarily know or give much thought as to whether variables are allocated on the stack or the heap. This is something you can get away with in some languages, but it's really something you should not misunderstand in C. I am constantly helping people debug issues where they have stack allocated a variable when it should have been put on the heap because they were planning to pass it to another thread or was supposed to outlive the function in which it was created, or something like that. And getting this wrong is a source of a lot of bugs in assignment and lab code that people ask me to look at. So the thing is, these are sort of different segments, and you can start to get a hint from that why, for example, in C, if you try to access memory outside the memory that you can legally access, it's called a segmentation fault. And yeah, you are well advised to know the difference when you're writing C code. So a full program really, in its runtime form, has different size segments, and the segments are made by the compiler. So some information here is set up by the compiler at compile time, and other stuff happens dynamically. But somewhere we have the code. These are the instructions of the program. It says, go here, do this, do that, do the next thing. All of those are parts of instructions. We have global variables. Global variables frequently get their own area, and this area is not unlimited in size, so we can't put everything in global variables. I've probably mentioned, and if I haven't, I've probably mentioned before, something about how, like in an exam question, we sometimes make use of global variables in a way that I wouldn't actually encourage you to do when you were working on real production code. That's just because, for the purposes of the exam, I want you to focus on using the thing correctly, not spending a lot of time figuring out how to make a struct and allocate it and fill it in and pass all the stuff to the other thread and figure out its deallocation later. Those are real life concerns, and those are things that you should do, and you shouldn't have excessive global variables, but in an exam question, we sometimes make an exception. And we have the heap. We have the stack, keeping in mind that each thread has its own stack, so there are potentially many stacks depending on how many threads we have. And then the standard C library stuff also is generally in memory, and other libraries could be there as well. Okay, so far so good. And the segments that are in your program from the programmer's perspective look something like this. Right, we have our main program, we have a stack, we have a symbol table that's used to look stuff up, and then we have some subroutines that are linked in, and square root, because the linker has taken the implementation of that from the library and added it to your application, recognizing that, hey, this is something we might want or need. Okay, so segments. Now, rather than thinking about memory as sort of a pure address, we can think of it as a tuple, a two-element item, consisting of a segment and an offset. And given that, we need some implementation to map it from this segment offset representation to the actual like linear, pure address, physical address form of memory. And the mapping for that is called the segment table. And just as we've seen before, the segment table has information about base, so the starting address of the segment, and a limit, the length of that segment. So typically we'll do some addition and some comparison to make sure that whatever address has been emitted by the CPU lies within that range. As you may also expect, because memory addresses are very common, the expectation is we need some hardware to make sure this is not painfully slow. And yeah, here's a diagram showing what happens. Right, the CPU issues an address. The first X number of bits, exact amount varies by implementation, represents the segment, and then the remaining bits, D, represents the offset. And so we'll go take a look in the segment table, so what corresponds to the limit and base for that particular segment, and we'll come up with the correct value that we're going to add to the offset. If the offset is invalid or we're outside the limit, then we'll report that as an error. Otherwise, we combine the value that is returned from the segment table with the offset that was issued by the CPU, and there we go. That produces the final address that goes out to physical memory. Okay, so that's actually pretty interesting, right? You know, it's like I dialed 555-1234, and the 555 is automatically replaced with the correct prefix, 123. And that prefix is the one that actually gets sent out to physical memory. Huh. How about that? So segmentation is cool, right? Segmentation means that memory doesn't have to be contiguous anymore, because when we're looking in this particular segment, well, listen, it can be represented by different parts of memory, and some of the time, for the 1234 example, we'll replace the 555 with 123, and for different parts, if it was originally 555-9876, then we could replace that with 456-9876. That would work. We can allocate different parts of the program in different segments, and different segments can be located in different areas of memory. And if you want to find out where something is located in memory, then we can use the address of operator, and we'll actually see potentially some interesting stuff. And I'll show you a quick example of finding out where stuff is located in memory. So I've written this program. It's not super fancy or anything like that, but we will just say, okay, two global variables, int global 2. We will have two stack variables here, and then we will malloc some heap variables, and then we'll just print their addresses, right? There's no reason this has to be fancy in any way. The goal is just sort of to take a peek and see what's happening. And this is not totally insane, all right? For sometimes, I've actually found it can be helpful if we print the values of pointers, because it gives us a hint as to like something going wrong. And if I ask you to print the value of a pointer and it's 0, it's like, okay, well that explains why we're getting this null pointer exception. Like, how did it get to be 0? But also, if we look at certain things and we see, that looks like a stack address instead of a heap address, that's a hint that something has been stack allocated that shouldn't be. And usually it's relatively easy to tell just by looking at the raw addresses if something is global stack or heap allocated, as we're about to see in this example. So yeah, let's give it a run. And we'll see global variables are located in one segment. The stack variables, they're located at actually quite a large number, and the heap variables are located nearby to each other in a different segment of memory, but not not next to each other, right? We'll notice that, like with the global variables, we'll see that, okay, there's 4 bytes between the two of them. The stack variables, because they're chars, there's 1 byte difference between them. And the heap allocated memory, I mean, they're close by, right? It ends, 1984 and 2016. Maybe we shouldn't get superstitious about those years. But we'll notice there's a couple of spaces between them, even though we allocated some characters. Another thing we'll also notice, if we run the program again, we don't get the same results, right? Like the offsets for some of these things may be different, and the global variables don't seem to move, but the stack and the heap variables do move from execution to execution. And some of that is like intentional as a security measure, making it hard to guess addresses. Is one of the security tactics that you might learn about in a computer security course, because it makes it a little bit harder to like mess with the memory of a program by feeding in instructions that overwrite memory that they shouldn't. A buffer overflow attack is quite specifically what I'm thinking of, and if you take a computer security course, you'll probably talk about that. But nevertheless, we can see pretty distinctly that, okay, like stack and heap variables are located kind of far apart in memory, and if I ever ask you to tell me about the values of pointer, and it looks like it's stack allocated when it shouldn't be, maybe we learned something interesting here. All right, so far, no matter what we've done, we've had fixed or variable size partitions, but they suffer from fragmentation, whether it is internal or external, as depended on the nature of what we're trying to do. And sometimes we've had some of each. Our new strategy is to divide up memory into fixed size chunks of equal size, and those are referred to as frames. And we'll divide the memory of each process into chunks of the same size as the frames, and those are pages. So any page can be assigned a frame, and a frame representing the physical memory could be empty, has nothing that's allocated in it right now, or it may have exactly 1 page in it. And the analogy, the way to think about it, the model for this is a simple picture frame. Like here's something you would get at IKEA or IKEA, depending on how you choose to pronounce it. And look, it's a container. You put a picture in it. You print out a picture somehow, or you buy a picture, something, and it goes in the frame. Okay. And any given frame may be empty. When you buy it from the store, it may come with a stock photo picture in it to show you the correct size, and for you to understand how great this frame could look if it had a picture of somebody else's family or a sunflower or something in it. That's a thing. But it has a picture in it usually when you buy it, or it could be empty. Either way, it could be empty or it could contain a picture. Both of those are fine. Now, if the picture frame is empty and we want to put something in it, well, that's very easy. We just put a picture in it, right? It's empty. There's nothing to do except add the thing we're adding. If there's already a picture in there, so you brought it home and it does have the stock photo of a sunflower in it, well, then you take out the picture that's already there, and then you're ready to use it. You could also just take out the picture to empty the frame, even without something to put in there immediately. Maybe you hate sunflowers for some reason. You've sworn revenge on sunflowers for what they did, and they know what they did. So maybe you've decided you hate sunflowers and you want to get rid of it, even if you don't have something to put in it immediately. If that's the case, that's fine. You just end up with an empty frame at the end of it. And a picture always has to be aligned to be completely in a frame. It can't be half in and half out. It can't be spread across more than one frame. Anything like that. Picture is always placed firmly in one frame. Now, if you expand this scheme to represent the fact that, okay, memory is bigger than one frame, so we have a very long row of picture frames. Each frame can contain one picture at a time at most, and a particular picture can be in at most one frame at a time. Okay, that's kind of our analogy for paging and how this is going to work. So when a process starts, it's loaded into memory and it has some initial memory requirements, right? Whatever is needed to start the program. So we have instructions, we have a default amount of space for the stack, we have some global variables, we have other stuff. All of that gets created. So we create the number of pages that are necessary to contain it. Over time, the number of pages can and will change as memory is allocated or freed. If we need to allocate more pages, we'll do that. If we need to deallocate pages because the memory that was in there is no longer needed, that's perfectly fine. And a process can also be swapped out to disk. To run it needs to be back in memory, that's fine. But either way, a process takes up a certain number of pages in memory at a given time, depending on its needs and what we have. Okay, so pages are very helpful because they separate the logical address from the physical address, right? As a programmer, if you have a 64-bit machine in which you have 8-byte pointers, you can pretend the address space of the computer is 2 to the power of 64 bytes, rather than being limited by the number of gigabytes of memory that happens to be located in the physical machine. So that's very helpful. So let's imagine then that we have something that looks like this. Initially, we have a very small, so it fits on the slide nicely, amount of frames that starts with 15 free frames from 0 to 14. They're labeled here, and if we load process A, and it consists of 4 pages, then it fills up 4 frames, A1, A2, A3, A0, all appear in frames 0, 1, 2, and 3. And if we load process B, its pages B0, B1, B2 appear in frames 4, 5, and 6. And same process C, it has 4, so C0 through C3 appear in frames 7 to 10. And if we swap out B and we want to load process D, and process D requires 5 frames, under some earlier schemes we would have a problem. But in this case, it's perfectly fine. We can just assign pages D0, D1, D2 to frames 4, 5, and 6, and pages D3 and D4 to frames 11 and 12, even though there's no contiguous block of 5 free frames. So that's pretty cool. This allows us to have multiple programs in memory, and they don't have to be contiguous, and we have a pretty good way of looking up where anything is. Thing is that when we have multiple segments for each process and they're no longer contiguous, a base and a limit address approach is not enough because there are many different pages and we don't know what goes where because it's no longer contiguous. So each process needs a page table to keep track of which pages are located where in memory, and we're also going to need a list of free frames. And so a page table diagram on a per process basis looks something like this. So process A has page table, and it says, okay, its pages are located in the following frames. The pages are shown as the left stuff outside the box, and then the frames that they're in are shown inside the boxes. Process B is swapped out according to the last step of the diagram that we were looking at, the one labeled F. Process C is in memory, and process D is in memory, spread across a couple of different areas. And we'll see also that there is now the free frame table containing a couple of frames which at the time are not filled. Okay. And so what we're going to do is use a page table to map logical memory to physical memory. Right, so when we have an address, if we identify that it's in page 0, we'll look at the page table, we'll identify that that corresponds to frame 1, and we'll translate the address that was emitted by the CPU to the physical address, which is going to land it in physical memory inside frame 1. For convenience, page size is usually a power of 2. Actual value is determined by hardware. I'd ask at this point, does anybody know what the determining factor would be? Give you a minute to think about it. Okay, so the determining factor is typically actually your disk drive. And based on how much you can transfer in one chunk to and from disk, you're going to choose your value probably to be exactly equal to how much you can transfer to and from disk in one chunk. For many systems, that corresponds to about 4 kilobytes. We'll talk about that a lot more as we get to I/O devices and stuff later on. In any case, the choice is almost always going to be a power of 2 to make it much easier to translate a logical address to a physical address. Otherwise, we have various headaches about what parts do we keep and what part do we cut off. So it's much easier if it's just a power of 2. Why does that make sense? Well, if the logical address space has 2 to the power of m, like 2 to the power of 32, let's say, and the page size is 2 to the power of n, let's say n is going to make it so we have 4K. Well, the higher order m minus n bits are the page number, and then the lower n bits are the page offset, right? And 4K is a nice number. Like I say, it typically comes from things we've got going on with the disk drive, but it's doable, right? It's going to be like 2 to the power of 12, so 2 to the n, n equals 12, which means that in a 32-bit system, the high order 20 bits are the logical address page number, and then the lower n 12 bits are the page offset. So we don't have external fragmentation because pages are always the same size in this scenario. And it also means we don't do any compaction, or at least we don't think about it. It's painful enough on memory, and it's excruciating in the will to do it on disk. There is a possibility of internal fragmentation. In fact, there will almost certainly be some internal fragmentation, but the amount of it is kind of limited, right? When you ask for memory, if it doesn't fit, okay, we allocate you a whole new page, and potentially we're wasting up to 1 page per segment, but that's not actually all that much in the grand scheme of things as far as we're concerned. So we'll usually just be happy with that. Right? If the memory required aligns perfectly with the page size, no memory is wasted. In a worst case scenario, yes, we have sort of 1 extra byte that results in the wasting of a page minus 1 byte. We'll take it. But internal fragmentation of 1 page, 4 kilobytes, is really not that much overall. Now, page size, as I say, does have an impact on this. If they're smaller, less memory is wasted in internal fragmentation, but it does mean more overhead. And pages have grown along with the size of main memory, but as we've already discussed, actually really what has caused a change in page sizes is more to do with what's going on with disks. It's most efficient for a read-or-write of a page to be 1 single operation as far as the disk is concerned. And when we do that, well, it makes them about 4 kilobytes. Okay, so now we finally have an explanation as to why things are the way they are. Why an application developer can treat main memory as if it is infinitely large and unshared, because we use a paging type system. And this results in scattering the program across physical memory. That's fine. But as far as the application developer is concerned, you can't tell. There's no difference. There's no way of knowing sort of what it would be. And bonus, we also get some protection in this scheme, right? There's no possible way to access memory that doesn't belong to us, right? Why not? Well, there's simply no way to make a request that is outside the logical memory space that we can access, right? Whatever address is generated, it could only be inside the page table. We'll look at the upper bits of it to make a determination about what page we're talking about. And if it's valid, great, continue, carry on. And if it's not, it's an error. But there's no way that we could ever issue an address that is somehow outside of our ability to do anything, right? It's not outside our area. There's no possibility of getting it wrong. So that's pretty cool. No matter what address is generated, it will be correct. It's like saying, yeah, no matter what phone number you dial, either you get a valid phone number or you get an error saying, sorry, the number is not valid. You can't dial something that's in a different area code. Do you want that? Maybe, right? This is a question of system design, and the answer, of course, is for our purposes, yes, we do want that. We do not want processes to be able to access things they shouldn't see, so we do like having this amount of protection in our system. But there's a little more complication to it. The operating system can manage the memory of all the processes, so it's going to need another scheme. The idea of sort of looking in the tables to check everything process by process maybe isn't super efficient. Maybe what we're actually looking for from the operating system's point of view is something that it calls the frame table. And the frame table is kind of the converse of the page table. It's just a listing of all of the frames indicating which page of which process a frame currently holds, if any. Right? And that gives the operating system a nice quick overview of who is where and who is what. And that's going to be more efficient than just having to check the page table for potentially hundreds of processes, right? Because we could always have many different processes running. So yeah, we like this better. Another great advantage of paging is the possibility of sharing of common code. Users very often have multiple programs open, and sometimes they are duplicates of the same process. Like if you have 2 copies of Microsoft Word open because you have 2 different documents open in Word, then yeah, those are both duplicates for at least part of the memory, right? Not everything, just part of the memory. Which parts? So the stuff that is like common between the two. And the stuff that's common, like the program instructions for Word, is the same. The content of your document is presumably different. I'm imagining you're opening 2 distinct, unrelated documents, so we should expect that those are different, but not true of everything, right? You might actually have the same document open twice, and that would be okay. We could reuse the pages there too, right? Whatever gets the job done. So yeah. In a multi-user system, also, different users could have different copies of the same program open as well. You're using Firefox, and somebody else is using Firefox. We could actually potentially reduce the memory that's being used by our system by reusing pages of things that are already in memory, as long as they're the same, right? They do have to be the same. We can't be cavalier about it. The memory actually has to be the same, otherwise this doesn't work. But it is nice if we can do it. And you might have heard when we talked about fork, how creating a new process creates a copy of the memory, but the actual practical implementation doesn't actually make new pages of all the memory. We usually end up with copy on write kind of behavior. And this is one of the ways in which the copy on write behavior is accomplished, and that is that we are basically saying, all right, share these pages, share these frames, until we have to make a change. So yeah, if you imagine there are 5 users on the system and they all want to use VI, let's say the program itself uses 10 pages, which is a made-up number. I have no idea how much it actually uses. I really have just made this up off the top of my head. And without sharing, each copy consumes 10 pages, so 50 pages are used in total. Whereas with sharing, we can share a lot of them and potentially save up to 40 pages of space. Now, maybe that doesn't sound like a lot, and truthfully, in the grand scheme of things, it isn't. But imagine doing this, with larger programs and how much you can save overall. It might actually be worth our while, right? That might actually be a reasonable savings added up over everything. Other programs are easily shared: compilers, libraries, operating system utilities, anything like that. In fact, any code could potentially be reused as long as it qualifies as reentrant. And reentrant is code that doesn't change when it's executed. There's no state maintained by the code. And I always give like a trivial example of non-reentrant code. A function that accesses global or static variables is non-reentrant, also sometimes called impure. And reentrant code is also called pure. And why is this example not reentrant? Well, reentrancy requires that we could pause it at any step of the execution, call that function again from a different thread with different values, and not have any change in the result. So that doesn't work in this case because if our timing is wrong and we overwrite the value of temp with that from a different call to this function, then we get the wrong answer in the initial call, right? That would make this non-reentrant. Obviously, if we change it so temp was stack allocated inside the function swap as opposed to a global variable, we would get a different outcome. And that would be fine, right? The code we're looking at here isn't necessarily wrong, but it's not reentrant, and you might even say not thread safe, depending on what you want to use it for. But code that is reentrant can typically, I mean not always, be shared between different pages. Now, in its simplest form, the page table is just a standard table. They look a little bit like the visual representation that we talked about earlier, where it's just listings of the different entries, and that's fine, but page tables can be very large. If the system is 32 bits and page tables are 4 kilobytes, so page sizes are 4 kilobytes, 2 to the power of 12, the page table has 2 to the 20 pages, which corresponds to about 1 million entries. That's more than I would like to go over manually on any given day. I got better things to do. But it is quite manageable as far as the computer is concerned. Scanning over 1 million entries is not too bad. With that said, there might be a need for structuring the table a little bit since this is fairly large. And we'll discuss 3 possibilities here. The first one is hierarchical page tables, the second is hashed, and the third is inverted. Each of those is, I would say, rather straightforward, but let's just sort of describe them. Hierarchical paging. Rather than having one big table, we just have multiple levels in the page table, so that the page table doesn't have to be contiguous in memory. We can just break it up and have the different ones represented in different parts. And if we have like a 2-level system, if then the page number is P, so the first, let's say 20 bits, the first K bits, let's say 8, represent the outer page. The outer page contains some information about where the inner pages are, so it tells us where to look for some more information. And then the inner page is represented by the remaining bits. And then after you identify the inner page, it tells you about the displacement, which is calculated. If you wanted to think about that with an analogy, it's kind of like if you wanted to borrow a book, and UW has several libraries, so the first part, let's say, of the information tells you which library is it in. Is it Dana Porter Library, or is it the Davis Center Library? And then the next part tells you about where in that library to look. And then finally, the offset identifies which specific book we're talking about. Something like that. The analogy is not perfect. There are certain limitations, if you will, to visualizing it this way. But I think that kind of gives a flavor of what it's like. Next idea, hashed page table. So instead of just having like a big array of entries, you turn it into a hash table. There's a hash function that assigns pages to buckets, and each bucket is implemented as a linked list. And then when you search for the particular page, you calculate which bucket it's in, and then you search the linked list to find what you're looking for. It's not too complicated. It would get the job done. But realistically, for the kind of situation that we face with a modern 64-bit computer, we can't really make a multi-level page table work, right? For 32-bit addresses, it's fine. With a 64-bit computer that has 4 kilobyte pages, the page table requires 2 to the power of 52 entries, and if an entry is 8 bytes, that means the table is more than 30 million gigabytes, or 30 petabytes, to use the appropriate prefix. That's a lot. Does your computer have that much memory? If so, can I borrow it? For non-nefarious, definitely not evil supervillainy purposes? Promise? Okay. Realistically, the inverted page table is going to make it a little bit easier to manage, right? We have 1 entry per frame rather than 1 entry per page. And the entry keeps track of what process it is and what page number that corresponds to. And this scales with the amount of memory that's actually in your machine, right? It saves a huge amount of space. For every gigabyte of RAM with 4 kilobyte page size, the page table requires only 2 to the power of 18 entries. Obviously, more when you have more RAM, but it's okay to have more overhead when you have more RAM because we have the space for it. And so this is actually fairly effective in helping to manage the amount of overhead that we have. There is a major drawback to this, though. And the major drawback is that it's no longer possible to easily find a physical frame location by looking at the address. Instead, we have to search the table, and the table is potentially large, so searching it may be slow. Who are you going to call? Ghostbusters. Memory addresses are, of course, like frequent, and as we've talked about on many occasions, even recently, we need some help. We need some help from the hardware people. Sorry, Ghostbusters. It's not something we can work around. So, for hardware support, we're going to, ask for help. And the simplest implementation uses a set of dedicated registers. Remembering, of course, that registers are the fastest form of storage. So when a process switch takes place, we just swap the registers that correspond to the lookups here with the ones for the new process that is going to run. The PDP-11 was an example of a system that had this. Addresses were 16 bits and pages were 8 kilobytes, and yes, it was a very long time ago. Stretching back in ancient history to a time even before I was looking at any of this stuff, but it was a strategy, right? The page table was 8 entries. That was a manageable amount that you could keep in fast registers, and you wouldn't sweat it too much if you needed to dedicate some hardware specifically to that. It's not always gonna. It's not gonna scale, right? The page table can easily be like 1 million entries or more, so it would be a little bit expensive to have a lot of registers. What we're actually going to do is have a more manageable amount, because if your CPU has 1 million registers, again, this is one I would like to borrow for definitely non-nefarious purposes. Not very likely that you have that. With that said, there is a distinct possibility that one day this video will be watched in the far future as some historical artifact of remember how computers used to be, when they only had 30 gigabytes of RAM, and somebody will look at this and they'll be like, oh, of course my CPU has 1 million registers, I can't imagine that it wouldn't, and it will be very funny, but we'll just have to wait and see. I don't know if the video will survive that long. It's fun to imagine that it will be, but probably not. Probably not. We'll see. We'll see. I do know that the slide, I think, that referenced this, does your CPU have 1 million registers or whatever, was placed in the Arctic Code Vault by GitHub. So there is a possibility, I guess, that, in the grim darkness of the far future, someone will look at that and wonder about what we were doing with our primitive computers of the time. Okay, never mind that. So the page table has to be kept in main memory because it's too big to fit in registers, and realistically that just means we can dedicate maybe one register to having sort of a handy shortcut to where the page table is, and we can go off of that as our strategy. Will it work? Sure. So to access a page from memory, we have to figure out where it is, and that requires, well, looking at the page table in main memory. And then after that, we can identify the frame, and then we go to the frame that contains the page we're looking for. Okay, so now we have two memory accesses that are required for every read and write operation. That's starting to sound like a problem, because going to main memory twice every time we want to do a read and write sounds like it would involve a lot of CPU time and a lot of effort, right? As far as the CPU is concerned, main memory is already pretty slow, and doubling the amount of time that it takes to read or write memory is going to be painful, right? That's going to be a problem. We don't like it already, so we're going to have to find a way to speed it up. And listen, you're not going to be surprised when I tell you here's the strategy that we're going to follow to address it. In fact, you won't be surprised at all, because we're doing the same thing that we always do, aren't we? We're going to get some hardware help. Hardware to the rescue again, a fast cache called the Translation Lookaside Buffer, TLB. And you can think of it as like a key value pair, so like a hash map or something like that, which makes it relatively quick to ask basically about where something is. And if we do that and we get the answer quickly, it saves us quite a lot of time. The key is the logical address. So when we put in the logical address, we get back the physical address as the output, and ideally this happens quickly. Now, to prevent this from being like absurdly expensive, we're going to have a limited capacity, and we can do the comparison on all items simultaneously, which is part of what makes it fast, because we can implement it in hardware, but our willingness to spend on hardware for the TLB is kind of the limiting factor in this regard. So it's usually something like 32 to 1024 entries in size, or at least it was at the time when I wrote this. It may have grown now on average to be a little bit bigger or a lot bigger, depending. But each of those things is expensive, so we are trading cost for time in this regard. Now, systems have evolved from having no translation lookaside buffer to having multiple levels over time if needed. And when a memory read or write is issued, we'll check the page number, and check means consult the TLB and see if the entry that we're looking for is in there. If the answer is yes, great, we're ready. We don't have to do anything else because the frame number that corresponds to that page that we're looking for is immediately known. If it's not in there, if we don't find it, we would call it a TLB miss. That is, it's not in there, and we have to look in the full page table, and that's going to be slower because we have to check memory, and we have to check it carefully, if you will. So, all right. Here's a diagram if that helps with sort of understanding. And so the CPU issues an address, and the address is split into the page number and the offset. The page number is concurrently checked against all of the entries in the TLB, as well as we ask the page table going to main memory. If we find it in the TLB, we can cancel the memory request, and we can just go off of what we need. If it's not there, then we're waiting for the result to come in from main memory, and we'll use that when it has arrived. Once it has arrived, either from the TLB or from the page table, we're going to combine the frame number with the offset to produce the physical address, and the physical address is sent out to the bus to actually request the data from physical memory. One of the things that's not shown on this diagram, but actually should be, is this idea that, well, if we had to go to main memory to get the value, we're going to want to remember that because we might need that page again in the future. And in fact, most likely we will need that page again, and not just, some vague time in the future, but probably very, very soon. So the element that's missing in here is that, adding this entry to the translation Lookaside buffer if we did get it from main memory. And the TLB, it turns out, is a specific instance of the strategy of caching. And if you remember earlier introductions to the idea of memory, we said, well, there's different levels of memory and they come at different speeds and different trade-offs. And one of the things we talked about was CPU cache. And well, caching is a critical idea, and it's so important actually that we need to take a digression from our discussion of memory in general to talk about caching. So that's going to be our next lecture topic.